Bismillahirrahmanirrahim. Today's topic is signal in correlation applications, and the course title is Principles of Communication Systems. I am Dr. Ishan Kaleem from ECE Department, CUI campus. Okay, let's discuss the lecture contents. Firstly, we will cover some examples related to the correlation, which we covered in last lecture, and the correlation practical applications, that how we can use that correlation in the practical applications. Finally, we will review Fourier transform and some of their examples. Okay, let's find the correlation of a signal. Let's start with an example. Find the correlation coefficient. We need to find the correlation coefficient rho between the pulse xt. This is the pulse xt given as, and the pulse is git, and there are number of pulses. There are 6 pulses, 1 2 up to 1 2 3 up to 6, as shown in the figure. This is 1 2 3 4 5 6, right? So we need to correlate this x of t first with the g1 of t, second with the g2 of t, third with the g3 of t, so on up to g6 of t. So as you know that to calculate the rho, we have an equation something like this one, like 1 over energy of a signal 1 into energy of a signal 2, right? And then there is an integral minus infinity to plus infinity, so signal 1 of t into signal 2 of t, right? So this I rewrite the general equation. So in this case we need the parameters. The first one is the energy of the two signals, right? So let's move on. So how to calculate the energy? We already calculated, we had already know the equation of energy, which we derived or which we presented in the um, chapter where we discuss energy and the power of a signal. Okay, let's start. So first we need to calculate the correlation between the x of t and the g1 of t. So we shall compute rho using that equation, this one, for each of the 6 cases. Let us first compute the energies of all signals. So first of all, we need to calculate the energies of the all signals. So for example, Ex of t, this is Ext. If you see, the range is 0 to 5 and the amplitude is constant, which is 1. So integral is from 0 to 5 and the signal is x square t. So because of energy there is a square term here. So if we put the value, x of t is 1, so 1 of square, if we take the square of 1, it's also 1. So integral of 1, so it is a, if we take the integral, so it will become t. So for example this one, so we need to put 0 to 5, so 5 minus 0, we have a 5 in, right? So energy is 5. So Ex has energy 5. Second, if you notice from the G1 of t, it is similar like x of t. So their energy will also be a 5. In the same way we find, as mentioned, Eg1, Eg2. If we find the energy of this signal, so instead of, because this is constant, 0.5, so 0.5 into 5, so it will be around 1.25 minus 0, right? So Eg3, it is minus 1, so we have energy 5. Eg4, Eg5, so on, right? For example, there is a energy they calculated for E minus 80, so which is E minus 280, and finally this one. Okay, let's start. So we determine the energy of E minus 80 ut over the interval t is equal to 0, t over 2 tau, right? Let's move on. For G4t, we have A 1 by 5, T5, and therefore EG4 we have energy this one. For G5t, we have T infinity, so we have energy 0.5. So by using that equation, we can find the energy, right? which we presented in the last slide. So energy of the last EG6 is 2.5 using sine square. So we need to integrate this. You have to check what is the integration of sine square 2 pi, then open it and put the value, so you will get 2.5, right? So first of all, we calculated the energy of each signal. Now from equation 2.5, which I presented in the last slide, you know that rho equals to 1 over E1, E2, 0 to 5, because the period is 0 to 5 instead of infinity, and 2 because their amplitude is 1. So 1 over 25 under root 5, so 5 into 5, 5 into 1 over 5, sorry, so you will get 1. So this is the correlation coefficient of x1 into g1. Similarly, for the correlation coefficient rho of second, like x2, x into g2, this is the correlation. So we need to, for energy of a G2 we have a 1.25, and the energy of the first one x is 5. So 0 to 5 and then 0.51. Similarly for the other signal, because there are 6, for sine there is last term is sine, so sine 2 pi t, you need to integrate and then this, and finally you will get 0. So from here we can notice that this one xt and this one is the last one, right? It is a sine. So from here you can see that they have a no similarity, because this is sine wave and this is just a constant value. So from here you can notice that we have a zero correlation. It means that they have a no similarity. In this case, if you compare this one with the first one, as there is some area, overlapping area, so this can be the correlation. There can be a correlation. So in this case we get the 0.628. Similarly for this one, if you compare this with x of t, so there can be a correlation in some phase, like some period, which can be this part. So here we also get the correlation 0.961. And in this case, if we compare this one with this, so you can clearly notice that this have a 1 and there is a minus 1. So they are opposite direction. So their result is minus 1. Here, because amplitude doesn't matter, the shape matters. So you can see that they have a maximum correlation 1, and similarly in that case as well. So we compare the x of t with 6 different pulses and different signals, and we find their correlation coefficient, and this correlation coefficient clearly indicates what is the similarity between the two signals. Now we have to move further. What is the application of signal detection? And what is the application of correlation in signal detection? So correlation between two signals is an extremely important concept. Why is it extremely important? Because it measures the similarity between the two signals. Up to now we studied this one. So this concept is widely used for signal processing applications in radar, sonar, digital communication, electronic warfare, and many others. So the same correlation concept is used in sonar, radar, and the other applications as well. How they use? Let's see. We explain this concept, for example, by taking an example of a radar. What is the basic phenomenon in radar? Whenever radar works, there is a signal pulse which is transmitted in order to detect the suspected target. For example, this is a pulse and this is the suspected target here, right? You need to detect the target, whether there is some target present or not, which is suspected one. So we transmit that pulse in this direction, and this will reflect and come back again here, right? So how can we detect that whether the object is present here or not? So this is the application of correlation here. How it works? For example, if a target is not present, there will be no reflected pulse. For example, if you see that, if you transmit from here and no reflection come back, then it means that there is nothing here, because reflection can only occur when there is some target or some object is present. So by detecting the presence or absence of the reflected pulse, we confirm the presence or absence of a target. So correlation of the received pulse with the transmitted pulse can be of great help in this situation. For example, if you transmit and receive, so if there is a correlation or the similarity between the transmitted wave and the received wave, then we can say that there is some target over there. Otherwise, we will say there is a no target. So a similar concept is used in digital communication, where we are required to detect the presence of one of the two known waveforms in the presence of a noise. So there is a problem of noise as well. If you transmit the signal and come back here, so noise will be added in the reflected wave as well. But we have to decide that there is only uh, reflection due to noise, or uh, or there is a in reality there is a target present. So we have to decide by using some threshold value. So if there is a value greater than, like if here we find the similarity, if the similarity is greater than some threshold value, we will call that the target is present. Otherwise we will call no target was present there. So let's see that mathematically. Consider the application of correlation to signal detection in radar, where signal pulse is transmitted in order to detect the suspected target. If target is present, pulse will be reflected by it. As I mentioned, if no target is present, there will be no reflected pulse, just a noise, because there will be no target, so we will get just noise, which will have a low amplitude as compared to the original transmitted pulse. So by detecting the presence or absence of the reflected pulse, we confirm the presence or absence of a target. The other problem is that by measuring the time delay between the transmitted and received pulses, we determine the distance of the target. You note that S is equal to Vt, right? So when we are transmitting any wave, we know the velocity of that wave, right? So it is known, and we by transmitting the pulse, and when we transmit and get back the pulse, so we know the time of that pulse, right? After, for example, 10 seconds, we get the pulse. So usually there is a 2, because it will cover the twice the distance, like going and coming back. So by using this, if we know both of them, then we can calculate the distance. So we confirm the presence or absence by measuring the time delay between the transmitted and the received pulses. We determine the distance S of the target. Let the transmitted and reflected pulses be denoted by GT and ZT. This is GT and ZT and GT as shown. If we were to use the equation directly, measure the coefficient, we would obtain this. But you know that if we will correlate ZT with GT, like the transmitted with the received, so if there is no correlation, then you will get 0. If there is a correlation, you will get 1 or some other value. But there is one problem here, because you know that when you transmit the pulse and the receive back again the pulse, so there will be some delay. So how can you notice that after a delay, when you will get the reflected pulse? So to overcome this issue, we will discuss on the next slide. We have a cross correlation function. What happens here in the cross correlation? Correlation is 0, because when we transmit the pulse right here and it comes back again, it will take time. So if we compare at the same time, like for example at time t, we did the comparison gt zt. So at the same time, we don't have a pulse. So it doesn't mean that the target is not present. So integral in the last slide will yield a 0 value even when the pulses are identical, but with relative time shift. Because there is a time shift, so we don't say that there is no target present, but there was a time shift. To avoid this difficulty, we compare the transmitted pulse with the received shifted pulse by t. Look at this, gt, and instead of only z small t, we have a z t plus tau. And what is this tau? Tau is the shifted version of the pulse. We not only in this way we not only detect the presence of the pulse, but we also detect the relative time shift with respect to gt. For this reason, instead of using the integral on the right hand side in this way, we use the modified integral called the cross correlation function of the two real signal. So this is called the cross correlation signal, but here zt is the pulse left shifted advanced by tau, as we already discussed in the properties section. So therefore is an indication of similarity with advanced, that is advanced by task setting. So autocorrelation is another way. The correlation of signal with itself is called the autocorrelation correlation. Look at this GT and again GT plus capital tau, because the tau is due to shift. So when we find the similarity between the transmitted and the same received signal, not between two different signal, it is called the autocorrelation. And for radar application or any other application, we can clearly understand from this picture. Look at this. We have a GT E minus T. So if we compare, you can see that at z of t, the pulse received after some time t second, right? This is t second. It is starting from t and ending at t plus t1. So if we compare this at this occasion, at this time period, for example, in this period we calculate the rho. So in this way, we will get the zero correlation. So it doesn't mean that the target was not present, but actually the problem is that there was a some time shift t second. So if we compare this one with the time delayed version by using this equation gt plus t tau, then there will be a similarity. So what we did, we just do the scanning. Like for example, this one is fixed, and we are moving this in this way and in this way. So wherever we have a more correlation, then like the more positive result or high result, so it means that the signal is present. So if by moving here and there we still didn't get any value, then it means that no signal or no target was present. So this was the concept of using correlation functions and one of the application in radar. And similarly, you can use this in number of applications. There is one other theorem presented by Parseval. So that's why it's called the Parseval's theorem. He says that you know that first of all, whenever you plot the vectors, this is starting from vector. So for example, this is a vector, so it can have a components. This component, for example, it can be created by a number of components, like this one, horizontal, vertical, and it is creating the third vector, right? So what he said that the energy of this signal, right, and energy of this component E of x, for example, and E of y, right? So he said that total E is the summation of its component, right? E of x plus E of y in general, right? It is clear. So if we have a n number of components, right? So this signal will be the total energy of the signal will be the sum of the total energy of the each component, like x, y, z, so on. Recall that the energy of the sum of orthogonal signals is equal to the sum of their energies. Sum of the orthogonal signals is equal to the sum of their energies. Therefore, the energy is the sum of the energies of the individual orthogonal component. These are orthogonals. So, total energy is sum of E1, E2, E3. These are the orthogonal components, and C1, C2 square, C3 square are their coefficients, right? So, that Parseval say that whenever you have a component, so when you calculate the total energy, sum the total energy of individual components, then finally you will get the total energy of a signal. This important result goes by the name of Parseval's theorem. So that was the concept that the independent component, orthogonal components energy, when you do the summation, you will get the energy, total energy, which is the signal energy, right? Okay, let's move to the Fourier series. You studied it many times, but there is a brief introduction here to just review the Fourier series. The basic concept is that for the periodic signals, we usually use the term Fourier series. And what the Fourier series do, the Fourier series convert the time domain signals. For example, this is a time domain signal. You have a time at x-axis and amplitude or the magnitude of the signal at y-axis, right? So whenever you have a function of a time and you want to convert this function of a time into function of frequency f, right? And then for a periodic signal case, we use the Fourier series. So here for the periodic signals, a decomposition in this form is referred to as a Fourier series. And for aperiodic signal, so this is periodic. Periodic means which is following this criteria, repeating after some time interval t. And for aperiodic, when there is a no constant period, so no repetition after a constant period of time, then for aperiodic signal we use a term called the Fourier transform. So this is the basic difference between Fourier series and Fourier transform. So, and what the Fourier series do? The Fourier series convert the time domain signal into frequency domain signals. Time domain graph shows how signal changes over time. In frequency domain, all the components, for example, frequency and amplitude of a sine wave, can be represented by a single vertical line. Let's see what does it mean. For example, you have a this sinusoidal which is repeating, right? This is with repeating with time, and you know that this repetition have a definitely have a frequency. For example, this repetition has a 2 hertz of frequency, right? And the magnitude is, for example, 4 volt, right? 4 volt minus 4 volt here, right? This is the time domain. When you took the Fourier transform or Fourier series of this signal, then what will you get? You will get a, because this axis is now frequency axis, right? So there is a 0, there is a 2, there is a 4, for example. So for this signal, if you plot it on the Fourier domain, right, in the frequency domain, so you will get only this wave. This point, you will get 4, right? So what you can clearly see that by if you have a number of sine wave components, but you convert into Fourier series, then only one component you have at the position 2, which represents the frequency, and the amplitude is 4, similarly as this one. So frequency domain is used to describe the domain for analysis of signal with respect to frequency rather than time. Frequency domain graph shows how much of the signal lies with each given frequency band over a range of frequencies. So this is range of frequencies. For the sake of clarification, I added here time and frequency domain signal. For example, there is a 10 periods of 1 volt signal with the 50 kilohertz sine wave, like the frequency is 50 kilohertz. So if we represent this on the time domain, this is time domain. And similarly, if you represent this on the frequency domain, so we have a 50 kilohertz and the amplitude is 1. Similarly, one here, but here you have a frequency 50 kilohertz. And here there is only time, so there is no plot of frequency. So you can clearly differentiate from this curve. This is too much cumbersome. There are a number of waves, but here you have only one wave and at the 50 kilohertz frequency. So this is a benefit of using Fourier transform or the Fourier analysis. Number of waves can be just represented by a single point. Okay, in mathematics, the Fourier series representation, Fourier series decomposes periodic functions or the periodic signals into the sum of a possibly infinite set of a simple oscillating functions named as sines and cosines. For example, you have a waveform which is not like a sine wave. So we by using Fourier analysis, we usually convert we convert the any periodic wave into sine and cosine. For example, this is the wave which is periodic, right? But it is not written in terms of sine and cosine. So Fourier, by using Fourier analysis, we can convert this into the by using we can use the sine waves and cosine waves. Another way we can say that we can use sine and cosine waves to construct that similar square wave pattern, right? So how can we do it? So there is, for a signal GT, for example, this is your GT signal, can be expressed by a trigonometric Fourier series over an interval of duration T naught. This is period. So, for example, we calculate these coefficients A naught, An, Bn, and by finding these coefficients, we can convert this signal, which is actually not a sine wave, and in other way around, by using this equation, we can convert this into sine and cosine. And what is the reason of converting or using the sine and cosine terms? The reason is that the analysis of sine and cosine terms is very easy. because number of algebraic expressions or equations exist which can by using that we can easily simplify the sine and cosine waves. So that is the reason of converging any wave into sine and cosine wave. So any periodic wave using Fourier transform. So by finding this coefficient a dot, a and b and so we can transform any signal into Fourier using Fourier series into in terms of sine and cosine. I think you already studied this in detail in other courses as well. So to find that coefficients, the a naught, a and bn, so you have to know the period and the waveform itself. So gt can be any waveform. So a naught you can find in this way. A naught is called usually the DC component, and a and bn are usually the harmonic components, like the high frequency components. So GT cos N1 is called the fundamental one, 2N is the harmonics, 3N, 4N, so on is the harmonic. So you can find this coefficient and then put into the previous equation, and when you put this into previous equation, it means that you are converting that, for example, the square wave in terms of sine wave, and then you can analyze easily. The other term is compact Fourier series, which is actually nothing new, but only the combination of uh, the Fourier series which studied before. As you know that a and bn, they are the two terms. So we, instead of using a and bn, we use only cn, right? And instead of using number of angles, we have only n omega naught t and the phase difference theta and an. So cn we can calculate the a n square plus bn square under the root. So in this way we can get the cn and theta tangent inverse minus bn over a. So in this way, you can write the previous equation in terms of compact form. This is called the compact form of the Fourier series. C naught is the similarly the DC term, n is equal to 1 to infinity, Cn cos n omega naught t plus theta n. The range is from T1 to T1 plus T naught. The other term is Fourier spectrum. You must know this one because this can be used a number of times in the literature. So there are two terms which is called amplitude spectrum and other term is called the phase spectrum. What is the difference between amplitude and the phase spectrum? For example, if you are plotting these Cn values versus f, Cn is the amplitude. So if you are plotting amplitude with respect to frequency, then it is called amplitude spectrum. And if you are plotting the theta n with respect to frequency, it is called the phase spectrum. These two plots together, that is the magnitude and the phase together, are called in general the frequency spectra of the GFT. So you must remember this term. The other thing is that when the Fourier series exists, so what is the condition uh, uh, we can calculate the Fourier series, otherwise it's not possible. So there are two conditions. So for the series to exist, the Fourier series coefficients, as we calculated in the previous slide, a naught, a and bn, must be finite. So these values should be finite. If one of them come infinite, then we can't calculate the Fourier series of that signal. From equation 2.76, it follows that the existing of these coefficients is guaranteed if gt is absolutely integral over one period. So when these a naught, a and bn is finite, so only condition is that when you will take the integral of the absolute integral over the one period of the given g of t, when it comes less than infinity, it means that the Fourier series exists. Existence of Fourier. So if we made this equation, this is known as the weak Dirichlet condition. So if a function g of t satisfies the weak Dirichlet condition, the existence of Fourier series is guaranteed, but the reason the series may not converge at every point. So it means that there can be some point in the g of t at which you will get infinite result. So it means in the end it will converge, but whole series may not converge at every point. So if a function has an infinite number of maxima and minima in one period, then the function contains an appreciable amount of infinite frequency component at the higher coefficients in the series. Don't decay rapidly. So the series will not converge rapidly or uniformly. The other condition is that the function can g of t can only can have only a finite number of maxima and minima in one period. If this condition is satisfied, that if you have a function g of t which has a maxima and minimum finite number of the maximum and minimum point in one period, then it may have only a finite number of finite discontinuities in one period. So when these two conditions, that the first one and the second one is met, then this is called strong Dirichlet conditions. So we know that in periodic waveform that can be generated in laboratories satisfies strong Dirichlet condition and possesses a convergent Fourier series. Thus, a physically possibility of a periodic waveform is a valid and sufficient condition for the existence of convergent Fourier series. So there are some examples like 2.8. I pasted the picture here. You need to find the compact trigonometric Fourier series for the periodic square wave. So this is a square wave given to you. You need to find the periodic Fourier series of this uh, figure, right? This wave, and have to sketch its amplitude and the phase spectrum as well. Amplitude means amplitude with respect to frequency, and the phase means phase with respect to frequency. So you need to calculate the Fourier first, and then using the compact Fourier series, right? Cn and the theta n, and then find the amplitude and the phase spectrum. Similarly, there is another example. You need to find the trigonometric Fourier series and sketch the corresponding spectra of the periodic impulse train as shown in figure this. So this is your example, and this is all. Thank you for listening, and for question answer there will be a separate online session. The exact date and time will be communicated later on. Thank you very much.